So we've already talked about the activity series, so we have a bit of an idea of what it is, how it works, and how to use it, but we didn't really get a chance to explain it or to understand why it works the way it works. And we're going to get a little bit closer to that today. We won't necessarily get all the way, we won't necessarily answer all the questions, but we're going to do a pretty good job of answering a lot of them. So where did we leave you off? Well, I left you with the question here of what is happening at the atomic level, and I asked you to think about what was actually going on to the atoms. And I'm sure that you are, that's been really bugging you, you've been thinking about it a lot. Pause for eye roll. But we want to actually start with that to say what actually is happening at the atomic level. So what we need to do is we need to look at each one of those pieces of the reaction and break it down individually. So iron 3 chloride, FeCl3, is an ionic compound that has one ion of iron with a +3 charge and 3 ions of chlorine, or chloride I guess, each one with a -1 charge. Zinc is a neutral atom. It's in its pure elemental form, and as we go across to the product side we find that iron is also a neutral atom with no charge, and zinc chloride, ZnCl2, is an ionic compound that contains one ion of zinc +2 and 2 ions of chlorine or chloride 1-. That's what's actually going on in the reaction. So if I write the reaction in that split up form, it ends up looking something like this, where I have broken the ionic compounds out into their individual ions, and then of course the elemental neutral elements are not broken out because they're atoms. They can't be broken down. If I take a look at the balanced chemical equation, not because we desperately need the balanced chemical equation, but in terms of looking at what's going on, the balanced chemical equation does actually help. If I do exactly the same thing with it and break it down, or actually include the balancing coefficient with each one of those ions or sets of ions, then it ends up looking like this, where I've got 2 ions of iron, 6 ions of chloride, 3 atoms of zinc, and by the time the reaction is done, 2 atoms of iron, 3 ions of zinc, 6 ions of chlorine. Okay, well that gets us a bit closer, but it doesn't tell us what is going on in the reaction. We now know what's going on with the atoms and ions on either side, but as the reaction progresses, what's actually going on? Well, we're going to follow the atoms as they go through the reaction. So iron starts out as ions of iron 3+, but they become iron atoms. In order for that to happen, what needs to have happened is that each atom of iron goes from a +3 to a neutral charge, a 0 charge, which means it has gained 3 electrons. Now there's 2 of those atoms doing that, ions, becoming atoms, so there's a total of 6 electrons in total that have been gained by the iron ions. Zinc, on the other hand, starts out as neutral, finishes up as an ion, and in that case what had to have happened was that zinc started out at 0, went to +2. That means it has lost 2 electrons each atom doing that. And then there were 3 atoms involved. That means each one loses 2, 3 atoms doing it, 6 electrons in total have been lost. Well, what about chlorine? Chlorine is actually kind of the one that's not really doing much of anything. It starts out as -1 ions and finishes up as -1 ions. So there's no change whatsoever in that ion, in the state of that stuff. And if you go back to our definition of a chemical change, which was making it new stuff, well, iron and zinc both undergo some kind of change from an ion to a neutral, or from a neutral to an ion. Chlorine doesn't. So it's easily arguable that chlorine is not actually involved in that reaction. It's just there balancing charges. It's just hanging out as what we call a spectator ion. So if I break it down to focus on the actual reaction, what is actually happening, I end up with this. Now, please understand, I cannot get a bottle of iron ions, or a bottle of zinc ions for that matter, so the chlorine has to be in there, but its only job was balancing charge. It's just hanging around doing nothing. It's like teenagers at the mall. If you're watching this during the pandemic, understand that joke normally kills. So, taking a look at the reaction for what's actually happening. Electrons are being transferred from zinc to iron. Or I could think about it slightly differently, that iron is attracting electrons away from zinc. And I like that phraseology because it should sound a bit familiar to us. We do have a tool that tells us about the ability of an atom to attract electrons, and that was electronegativity. Okay, so if I look at the electronegativity numbers, can I use those to predict? Can I use it as a bit of an explanation as to what's going on and why certain reactions are spontaneous and other ones are not? Why certain metals are higher up on the activity series and other metals are lower down? So I looked up electronegativity for iron and zinc, and I found out this, not massive differences, but a slight difference between them. Iron is more electronegative than zinc, and what that means is iron has a greater attraction or a higher attraction for electrons than zinc does. So if I take a look at the reaction, then if I can say that in that reaction iron is attracting electrons away from zinc, then I have my explanation. So if I go back to that reaction, let me go back to it. Okay, I don't have it here, but in that reaction, iron attracted electrons away from zinc, just like electronegativity tells us it should be able to do. Let's go to this one where I do actually have the reaction written out. Okay, we saw this one earlier, and we used it with the activity series, and we saw it had no reaction because tin was lower on the activity series scale than iron was. So iron was not going to push tin out, or the other way around, tin was not going to push iron out because tin was less reactive. Does that work with electronegativity? So, looking up our numbers again, I know iron from before, 1.8. Tin ends up being 2.0, so tin is more electronegative than iron. Tin holds onto its electrons more tightly, or I could say iron has a lower attractive force for electrons than tin. Does that matter? Well, if I were to try and do that reaction, yes, I could write it on paper, but in order for that reaction to happen, iron would have to take electrons away from tin. So tin has electrons right now, it's neutral, and it has electrons, let's say, available to lose so that tin becomes a positive ion, but iron does not have the ability, does not have the electronegativity, does not have the attractive force to pull electrons away from tin. So at that point, the reaction as it's written cannot go forward because it would require iron to take electrons from tin, so I would say no reaction. Okay, now that's a lot of words to say the same kind of thing, and hopefully it looks a little bit repetitive because I want you to find the one that works for you. Okay, so short version of what's going on. The metal that has a higher electronegativity is going to end up with the electrons. It's going to end up in the neutral state because metals react by losing electrons. So if the metal starts out in a compound, positive charge is an ion, it will then react to take electrons from something else and end up neutral. But if that metal starts out as an element where it has electrons, quote unquote, available to be lost, if it has the electrons and it's neutral, it's going to keep those electrons if it has the greater electronegativity, at which point we would say no reaction. Okay, let's try a couple. I'm going to get you to pause the video after you've seen them and see if you can predict them. So I'm going to give you a list of metals and their electronegativities, and I'm going to give you 3 different reactions. Okay, and you decide whether or not the reaction would go forward or not. This is a great moment to pause the video, and we'll check with you when you're done. So if you pause the video and if you worked it out, you would have found that copper, being more electronegative, starting out with a positive charge, is going to take electrons away from zinc, and the reaction would continue. Aluminum has a lower electronegativity than zinc, so it's not able to pull electrons away from zinc. Zinc hangs on to those electrons, no reaction. Whereas in the last one, zinc has a lower electronegativity, iron has a higher one. It's kind of similar to one we saw earlier. So iron does take electrons away from zinc, and the reaction continues as written. I want to pause just for this moment, or at this moment, and that last reaction, we actually make use of that reaction quite a bit. If you have a boat or something like that that's in the water a lot and it has some iron or steel parts to it, there is usually what's called a sacrificial anode that prevents the iron from rusting. It actually uses that reaction, usually. Okay, where did we finish up? Here's where we're at. We hopefully have a way to explain, other than just using the chart on the activity series, but that's still a worthwhile thing. But then we should be able to explain why something is spontaneous or not. By the way, it doesn't work all the time. If you found two metals that have the same electronegativity and you put them in a reaction, chances are one of those will be spontaneous and the other version won't be. So electronegativity is an important piece of the picture, but it might not be the complete picture. But we'll worry about that another time. Talk to you then.